Hello, and welcome to our second lecture in the Einstein Club program. And this is going to be a preview of what is to follow in lecture number 2. I trust you found lecture number 1 to be quite interesting and stimulating, where we discussed the George Polya methods that we could be using to solve problems. In lecture number 2, we're going to apply these ideas in actual problems. And one of the problems we're going to expose you to is Euler's formula for polyhedra. Euler. Euler was a famous Swiss mathematician. You pronounce his name as Euler, Leonhard Euler. He was a Swiss mathematician, and he discovered an interesting relationship between the vertices, faces, and edges of a polyhedron. Now, what do you mean by vertices, faces, and edges? Vertices are the corners. So if you look at this block here, that's a vertex. It's a corner. The face is the surface here, and there are 6 faces on this guy here. And the edges are these lines at the ends here where 2 faces meet. So if you count in each of these blocks, how many vertices, faces, and edges do we have? Well, this one would have 1, 2, 3, 4 on the back there, 5, 6, 7, 8. 8 vertices. How many faces? 1, 2, 3, 1 underneath, 4, 1 behind, 5, and 1 behind, 6. There are 6. And how many edges? Well, it's 1, 2, 3, 4. 4 below it. It's 4 plus 4, 8. And you also have these 4 going downwards, 1 on the back. So there's altogether 12. Now there's an interesting relationship you can discover about this. And we'd like you to fill in the blanks in the table here for all these shapes that we have. Right? So if you take shape A, it has 8 vertices, 6 faces, 8 vertices, 6 faces, and 12 edges. Now carry on doing that for the rest of the shapes and see what you come up with. It's easy to count. But what we are getting at is that, is there a relationship? Is there a formula linking the vertices, faces, and edges? There is actually. It's quite intriguing. Can you see with the eyes of Euler? There's an interesting play on the word see there. Read about Euler and you'll see why the word see is so relevant in the discussion. So now let's go on to another important result. Similar idea. Well, you see these Platonic solids. These are solids which have got faces that are identical. For example, the first guy here is a tetrahedron. Tetrahedron. The second guy is a cube. You know him very well. Then you got this guy, and that guy. There are only 5 of them. Actually, there are only 5 in existence altogether. There's a reason for that, but we won't discuss that in detail in our lectures. Now, here's a very interesting sideshow from the Euler's formula for networks. Now let us draw a shape, any shape, say like that. And we draw one line inside it. It doesn't have to be a straight line, it could be curved. Where the curve meets the other shape, let's call it a vertex. So there are 2 vertices in this problem. And these things, we shall call them faces, 1, 2, and outside is a 3rd face. Face is 3. Edges will be these things here on the outside, 1, 2 edges. So there are 2 edges, vertices. Well, no, sorry, there's a 3rd edge here. There's 3 edges. What about the middle guy, right? Now there's a relationship between the vertices, faces, and edges there. If I make the diagram slightly more complicated, let's take a similar thing. It doesn't have to be a perfect shape, but let's take something of this type. Now, there's 1, 2, 3, 4, 5. There seems to be 5 vertices. How many faces are there? 1, 2, 3, 4. Those are the spaces, the different regions. And the outside one is the full space. We call that the fifth one. And lastly, how many edges are there altogether? Let's count up. 1, 2, 3, 4, 5, 6, 7, 8. So, is there a formula linking the vertices, faces, and edges? Well, who knows? We'll come across that in the lecture. Then we shall move on to problem solving. The first question there is, what is the difference in this case here? You have to fill in the numbers 0, 2, 3, 5, 8, and 9 in the blocks to make the highest possible difference. Highest possible difference. So I think it makes sense that you should have the biggest number on the top and the smallest number below it. Then your answer will be highest. Okay, so what is the biggest possible number you can get from these 6 digits? And what is the smallest? Remember, you cannot have a number like 0, 8, 9. That's not allowed. Right? Numbers don't start off with a 0. You can have a 0 in the middle or in the end, but not at the beginning. Anyway, you find that out. Newspaper boy. In each day, a boy sold 3 more newspapers than the day before. By the 8th day, he sold a total of 100 newspapers. Total, right? It's a total of 100. How many did he sell on the 8th day itself? Well, there are many ways of thinking through this, but you can try to understand this first by guessing. Let's take a wild guess. Let's suppose he sold 1 on the first day. Okay, let's call this day 1. He sold 1. Day 2, he sells 3 more. That's 4. Day 3, he sells 7. And so on and so on and so on. Come down to the 8th day. I don't know how many he sold, but we'll end up with a certain number there, and we'll get the total. We're supposed to get 100. Now, what if we don't get 100? Then the answer we get, the wrong answer we get, will help us to refine our guess. Our guess was 1 at the start. So the answer we get will help us to make a correction if that's not going to work out. It may work out, who knows? I won't tell you right now. Checkmate. Examine the pattern in the squares shown. The first, second, and third patterns are shown. How many black squares will be in the 50th pattern? Now, in the first square, you got, it's a 1 by 1. This one has got, it's a 3 by 3, the next one. See, there's 3 this way and 3 down. But there's actually 2 black squares on each side. This one has got 3 black squares on each side. 1, 2, 3. Right? So you've got to discover some kind of a pattern to move on to the 50th. I think it makes sense for you to understand that the 50th one will have 50 black squares on each column. The 50th pattern will have 50 black squares on each side. But how does it help us to solve the problem? Well, you can think about that very carefully. Wicked calculation. Calculate 14 times 19 plus 19 times 19 minus 23 times 19. So now, what you can observe is that the 19 appears 3 times. That helps us to find a quick way to solve this problem without going into lots of calculations. How can we do it? You think about it. Fine, and then moving on to the next one. Crazy birthday quote. Today, Anna is 18 years old. The day before yesterday, she was 17. However, next year, she will be 20. She was not born on February 29th, and her age is in human years, not dog years. How can this be? Well, the trick here is to work out what is today. Work out today's. Don't worry about the year. What day is it? Is it the 1st of December? Is it the 30th of December? And what was yesterday? So once you get to understand these things, you'll see how this can actually work out. It will be discussed in the lecture. This one I wouldn't say much about. You think about it. 2 mothers and 2 daughters go fishing. Each person caught a fish. There are 3 fish altogether. How can this be? A man is 80 centimeter plus half his own height. How tall is he? Not so difficult for you there. I don't have to say anything. Then it takes a man 1 hour to dig a hole 2 meter long, 2 meter wide, and 2 meter deep. How long will it take him working at the same rate to dig a hole 4 meters long, 4 meters wide, and 4 meters deep? So 2 meters becomes 4 meters. So do you think the answer will be double? Well, think very carefully about this. He's not only digging straight down, he has to dig sideways as well. So he's got more work to do, and so he might need more time than just 2 hours. So think through that problem and see if you can come up with a solution on your own to the number of hours he needs to dig such a hole. Quick joke before you leave. If it takes 1 hour for a man to dig a hole, how long does it take to dig half a hole? Half a hole? Did you say half hour? No, there's no such thing as half a hole. Any hole is a hole, a full hole. Great. Okay, so that's a joke to end off with. We'll see you then in the actual lecture online.